Supramolecular chemistry, non-covalent interactions in host-guest complex formation. Supramolecular chemistry, a term formalized by Jean-Marie Lehn, is broadly defined as the chemistry of molecular assemblies governed by non-covalent interactions, often described as chemistry beyond the molecule. It encompasses the organization of discrete molecular entities into higher-order architectures through intermolecular forces such as hydrogen bonding, electrostatics, pi-pi interactions, and van der Waals forces. In its simplest form, supramolecular chemistry involves the formation of a host-guest complex, wherein a molecular host bearing convergent binding sites interacts with a complementary guest possessing divergent binding functionalities to yield a well-defined supramolecular structure. This concept bridges molecular structure and function, extending traditional covalent chemistry into dynamic, reversible, and adaptive systems. Historically, the conceptual foundations of supramolecular chemistry can be traced to the late 19th and early 20th centuries, notably the coordination theory of Alfred Werner, the receptor concept introduced by Paul Ehrlich, and the lock and key model proposed by Emil Fischer. However, the field emerged as a distinct discipline in the 1960s to 1970s with the advent of synthetic macrocycles, particularly crown ethers discovered by Charles J. Peterson, followed by cryptans and spherans developed by Donald J. Cram and Lehn. These advances established the principles of molecular recognition and selective binding, ultimately leading to the awarding of the 1987 Nobel Prize in Chemistry to Pedersen, Cram, and Lehn. Since then, supramolecular chemistry has evolved into a highly interdisciplinary field, underpinning developments in nanotechnology, materials science, and chemical biology. Supramolecular systems are commonly classified based on host-guest topology and interaction modes. Hosts with intrinsic cavities, such as cavitans, form inclusion complexes, cavitates, whereas clathrates arise from lattice-like assemblies in the solid state where guests are encapsulated within intermolecular voids. A further distinction is based on interaction strength and directionality. Systems dominated by electrostatic and directional interactions are typically termed complexes, while those stabilized by weaker, nonspecific forces are often referred to as clathrates or inclusion compounds. Beyond host-guest systems, self-assembly processes describe the spontaneous organization of complementary molecular components into ordered architectures without predefined host-guest roles. The principles of molecular recognition in supramolecular chemistry are rooted in receptor-substrate interactions, coordination chemistry, and the lock and key analogy. Fischer's lock and key model emphasizes geometric and stereoelectronic complementarity between host and guest, forming the basis for selective binding. Werner's coordination theory generalizes this concept through metal-ligand interactions, while Ehrlich's receptor theory underscores the necessity of binding for function. Together, these frameworks describe how specificity arises from a combination of structural fit and intermolecular affinity. A central quantitative parameter in supramolecular chemistry is the binding constant, K, which reflects the thermodynamic stability of a host-guest complex. It is defined by the equilibrium between free and bound species and is commonly determined using spectroscopic or titrimetric techniques. Large binding constants correspond to strong affinity and stable complexes, and they serve as a key metric for evaluating molecular recognition and selectivity. Thermodynamic selectivity is typically expressed as the ratio of binding constants for competing guests. The stability and specificity of supramolecular complexes are governed by several interrelated concepts. Cooperativity refers to the synergistic interaction of multiple binding sites, where the overall binding affinity may exceed positive cooperativity or fall below negative cooperativity, the sum of individual interactions. This phenomenon is closely related to the chelate effect, wherein multidentate ligands form more stable complexes than their monodentate analogues due to entropic and enthalpic advantages. Preorganization further enhances binding efficiency by arranging binding sites in an optimal geometry before guest association, thereby minimizing conformational and desolvation penalties. Complementarity, both geometric and electronic, ensures that host and guest interactions are maximized, reinforcing selectivity and binding strength. Thermodynamically, supramolecular interactions are governed by the balance of enthalpic and entropic contributions to the free energy of binding. Non-covalent interactions such as ion-ion, ion-dipole, dipole-dipole, hydrogen bonding, cation-pi, anion-pi, and pi-pi interactions collectively determine complex stability. Solvent effects play a crucial role, particularly in polar media, where competition for binding sites is significant. The hydrophobic effect, especially in aqueous systems, is a major driving force for complexation, arising from the release of structured water molecules and the minimization of solvent disruption. Supramolecular chemistry encompasses a diverse range of molecular families characterized by their structural features and binding properties. Macrocyclic hosts, such as calixarenes, crown ethers, and cryptans, provide well-defined cavities for ion and molecule recognition. Cyclodextrins, derived from cyclic oligosaccharides, exhibit amphiphilic cavities suitable for encapsulating hydrophobic guests in aqueous environments. Cyclophanes and cavitans offer rigid, pre-organized frameworks for selective inclusion. Flexible acyclic systems such as podans serve as simpler analogues with reduced binding efficiency. Highly pre-organized hosts like spherans exhibit exceptional selectivity due to minimal conformational rearrangement upon binding. Beyond discrete host-guest systems, mechanically interlocked molecules such as catenanes and rotaxanes represent advanced supramolecular architectures with dynamic and functional properties, forming the basis for molecular machines. In its modern form, supramolecular chemistry represents a unifying framework that integrates synthesis, structure, dynamics, and function through non-covalent interactions. Its rapid growth and interdisciplinary reach continue to drive innovations across chemistry, biology, and materials science, positioning it as a central discipline in the design of complex functional systems.